All right, so now let's talk about strong acids versus weak acids, strong bases versus weak bases. Okay. A strong acid, so certain compounds are considered strong acids, and that's because when you put them into solution, 100% of that starting material will ionize into its two components. So hydrochloric acid is an example of a strong acid. If we look here, what this image is showing us is we're adding HCl to water, but at the end, 100% of that is converted into the chloride ions and the hydronium ions. There's no HCl that's actually left over. 100% of them has been broken up. This is another way of saying this equilibrium greatly favors the product, right? It has a super high equilibrium constant. Because of that, because that ionization happens completely, it makes it a little bit easier in terms of the fact that your concentration of acid is then equal to the concentration of the hydronium ion, right? So the concentration of acid that you started with, 100% of that has been converted to hydronium ion, okay? A strong base is a similar concept. So sodium hydroxide is an example of a strong base. What makes a base a strong base is that when you dissolve it in water, 100% of it dissociates into its hydroxide ions. Again, a reaction that greatly, greatly favors the products. So likewise, if I prepared a solution that I know my concentration of sodium hydroxide is 1 molar, for example, then I know the concentration of hydroxide ion after it's been dissolved is 1 molar. Okay, so for strong acids and strong bases, the concentration of acid is equal to the concentration of hydronium ion. Likewise, for strong bases, the concentration of that base is equal to the concentration of the hydroxide ion. Weak acids are kind of the opposite. They're in more of a dynamic equilibrium where the reaction doesn't very strongly favor the products. There's still a considerable amount of reactant left over. So hydrofluoric acid is an example of a weak acid. We see when we combine hydrofluoric acid and water, you have some of it that dissociates. So this one here dissociated, but a lot of it remains as hydrofluoric acid, the undissociated form, right? So these are reactions that don't have very high equilibrium constants. They don't strongly favor the product side. These would be considered weak acids. So for weak acids, we can't say that the concentration of HF is going to be equal to the concentration of the hydronium ions. We can't say that. We can only say it for strong acids. So these are actually all examples of weak acids. There are a ton of them. Okay, most acids are weak acids. So rather than trying to learn what acids are weak acids, we're going to learn the very small list of strong acids. Anything else will be considered to be a weak acid. So these 7 here are the list of strong acids that you're going to have to have memorized. Okay, so that sounds like a big task, but let's just pick this off here. HCl, HBr, and HI, these are all hydrohalogens, right? So if we look on our periodic table, chlorine, bromine, and iodine all live in the same block. So if I have an ionic compound between any of those and hydrogen, that would be a strong acid. So notice that fluorine is kind of the exception. Okay. So these kind of all can fall into the same category in your brain. Likewise, I have 2 of them that correspond to polyatomic ions that you were supposed to have memorized. The nitrate ion, its acid is a strong acid, and the sulfate ion, its acid is also a strong acid. So nitric acid and sulfuric acid are both strong acids. And then the last 2 are ones that I didn't tell you that you have to have memorized, but they're chlorate and perchlorate. And so you can see their formulas are really similar. There's just differ by 1 oxygen. So HClO3 and HClO4 are also strong acids. So this list of 7 strong acids is something that you just have to have memorized. Any acid that is not a part of this list would be considered a weak acid. we also have this concept of weak bases. So we saw ammonia playing the role of a base in a few reactions, but similar to this concept of of weak acids, a weak base means that yes, some of it will dissociate into hydroxide ions and ammonium ions, but most of that ammonia remains NH3 in solution. Again, this is just what we would consider to be a dynamic equilibrium, or an equilibrium where the neither side of the reaction is very strongly favored. There's still an appreciable amount of both products and reactants in there. That would be considered a weak base. Okay, so most of our weak bases have a nitrogen in there, which is the atom that's actually accepting that proton. Remember, bases accept protons. Most weak bases have nitrogen in them, and then we can always sort of draw that conjugate acid by adding that extra hydrogen and increasing its charge by 1, right? So this would be the conjugate acid of this particular base. But just like with our strong acids, for our strong bases, we're not going to try to learn all the different weak bases. We're just going to learn the smaller list of strong bases. So that's pictured here. You can see they're all salts that have hydroxide. All right, but it's actually even a little bit easier than this. We're going to say that a strong base is any soluble hydroxide, right? So if we look at our solubility table here, we saw that actually most hydroxide compounds were insoluble. That's what this table was telling me, with the exception of these here, right? And so these soluble exceptions to the hydroxide will be your strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, barium hydroxide, or ammonium hydroxide. Those would all be considered our strong bases. All right, so how do we use this information? Well, we're going to be able to calculate the concentration of hydronium ions and hydroxide ions for a solution. These are all strong acids. So remember, I can just say that my concentration of HNO3 is equal to the concentration of the hydronium ions. Concentration of the strong acid is equal to the concentration of hydronium ions. So in these examples here, finding the concentration of the hydronium ion is going to be very easy. That is just going to be equal to the concentration of the acid. So this would be 0.0311 molar. This is going to be 4.51 times 10 to the negative 5 molar. And this is going to be 8.74 times 10 to the negative 6 molar. Okay. It also wants me to find the hydroxide ion concentrations. How am I going to do that? For that, I'm going to need to use that expression that hydronium times hydroxide is equal to that 1 times 10 to the negative 14. Okay. I'm not even going to write the 1. Is equal to 10 to the negative 14. Okay. And we're going to consider this to be like an exact expression. We're not going to let this limit our number of sig figs. So I'm going to just have to rearrange this equation to solve for the hydroxide ion concentration. I'll divide both sides by H3O plus. That'll cancel it out on this side. Oops. And so I'm left with this expression here. So in order to find the concentration of hydroxide ions in each of these, I'm going to have to take that hydronium ion concentration. I'm going to have to take 10 to the negative 14 and divide it by the hydronium ion concentration. So this would equal 10 to the negative 14 divided by 0.0311 equals 10 to the negative 14 divided by 4.51 times 10 to the negative 5, and equals 10 to the negative 14 divided by 8.74 times 10 to the negative 6. Okay, So if I did that for each of these and punched it into my calculator, I would get that my hydroxide ion concentration is 3.22. Sure, I got a number of digits. Actually, I'm going to have to move this down. Three point 215, 3.215, 4 times 10 to the negative 13 molar. I have 3 sig figs, so this would be 3.22 times 10 to the negative 13 molar. Punch this into my calculator, and 10 to the negative 14 divided by 4.51 times 10 to the negative 5 is 2.21729 times 10 to the negative 10 molar. Just make some room for myself. So again, I have, for all these problems, really, you can see that I have 3 sig figs. So I'm going to report my answer to 3 sig figs. So this would be 2.22 times 10 to the negative 10 molar. This is a good problem to punch into your calculator to make sure you're getting that answer. If your 10 to the negative whatever is different than mine, it's because you're not punching it into your calculator correctly. Remember that when you're going to divide by something in scientific notation, most of the time, depending on how you punch it into your calculator, but it's always safe if you put it in parentheses. So for the last one, I'm going to take 10 to the negative 14 and divide it by that 8.74, and I will get times 10 to the negative 6. I'll get 1.14416 times 10 to the negative 9 molar. Round that to my 3 sig figs, 1.14 times 10 to the negative 9 molar. It's my final answer here. All right, so now we have another one, but these are now our strong bases: lithium hydroxide, calcium hydroxide, and potassium hydroxide. Remember that what a strong base does is it makes it so that it's really easy to find the concentration of hydroxide ions. In this case, it would just be the same as what's given for the concentration of lithium hydroxide. For this one here, I'm going to assume that all of my base dissociates. The thing that's tricky about this is I have 2 hydroxide ions per calcium hydroxide molecule, right? So that means I have to take this concentration here of calcium hydroxide and multiply it by 2 in order to get the hydroxide ion concentration. So this would be 8.30 times 10 to the negative 5 molar. All right, potassium hydroxide, I don't have to worry about that. That's just the same, 8.74 times 10 to the negative 6 molar. And again, the complication here came from the fact that in calcium hydroxide, there are 2 moles of hydroxide ion per 1 mole of CaOH2. All right, so that's why I had to take that concentration and multiply it by 2 to account for that. In order to get the hydronium ion concentration, I'm again going to use this familiar formula. Right, in this case, because my variable that I'm solving for is the hydronium ion concentration, I'm going to divide both sides by the concentration of hydroxide. That will cancel it on this side, so I'm just going to erase. All right, and I'll see that my hydronium ion concentration is equal to 10 to the negative 14 divided by the concentration of hydroxide. So A, B, C, A, B, 10 to the negative 14 divided by the 0.0311 molar. Actually, I'm not going to put the units in there. The units for the concentration will just always work out to be molar. This time is 8.30 times 10 to the negative 5, and 10 to the negative 14 times 8.74 times 10 to the negative 6. All right, so I always sort of go the long way where I put down the whole number and then I round it to the correct number of sig figs. In the interest of time here, I'm just going to give the answer to the correct number of sig figs. This would be a hydronium ion concentration of 3.22 times 10 to the negative 13. This one would be 1.20 times 10 to the negative 10. And this is 1.14 times 10 to the negative 9. All right, so make sure that you can punch that into your calculator and that these particular examples make sense.